Okay, this is our sessions plan for all the 6 sessions we have in this project. And today is the 4th session, so we will start with the attention mechanism. This is the outline I have for today's session for the theory part, and we're gonna start right away with attention cues. And if we think a little bit about attention, the most or one of the important things to remember is that human attention itself is limited and a valuable commodity. And that's why it's also being researched in the context of economics. We live in an attention economy, and a lot of business models actually capitalize on that fact. So for example, in the music and video streaming market, we either pay attention to ads or we pay to remove those ads so that they don't take our attention away. Similarly, video games, we can either pay attention and level up our character. So we have to really focus on the game, or we can just pay to gain experience. So you would probably pay to gain some XPs or some items that um, you otherwise wouldn't be able to get. So there is really an economy of, do I pay with attention or do I pay with money? So these things can be interchangeable. And um, what's also really remarkable is that in nature, information isn't scarce. We get bombarded by information all the time. What is scarce is really attention that we pay to certain information. So for example, our optic nerve receives 10 to the power of 8 bits per second, but that's way too much information that we could ever process with our brain. And one key insight is that not all input information is really equally important. Some things won't just be important. For example, with our eyes, when we focus on something, usually what is in the periphery is blurred because we don't need to know the details of what's on the side. But the capability of filtering information by its importance allows our brain to allocate the resources in a much more smart way. And there have been some really clever people who developed an attention model. The one we are going to talk about first is William James, who proposed this model in the 1890s. And the idea or the framework really distinguishes between two types of cues or information. The first one is non-volitional. And what it means is just that it, it takes our attention because of the saliency of an object, or by its inherent properties. We will try to, or we will pay attention to it whether we want it or not. So a good example for that is a red cup of coffee, as you can see here on the right side. And that is because the red color will naturally attract our attention to it. And there are many, many examples out in nature. And one very famous example is road signals. So red attracts our attention. So that's why the stopping signal is red. It's because we will see it and we will know that we shouldn't cross the road at that time. The second type of cue is called volitional. And this is based more on our cognitive and volitional controls. So volitional here really means that we have some, or we exert some control over it. And the simple example that is given in the book is that we want to read a book. So to do that, we first need to focus our attention to the location of the book first. So this is shown here in the right figure. And really the key distinction here is that this is task driven. So we wanted to achieve something. So we shifted our focus to that object. And it turns out that we can combine both of these cues to design an attention framework. So what really differentiates the attention mechanism from the fully connected layers that we've been discussing so far is that we add here these volitional cues. And what's going to happen is that we're going to let the keys, so the non-volitional cues and the queries, the volitional cues, interact with each other to generate, as we will see later, um, some scalar values, which will tell us how much attention we should put to each value or the sensory inputs here. And by just summing up over these, we will get our output. One thing to note is that we have as many keys as we have values here. So really, we are just gonna try to calculate how much attention we have to pay to each value here by using this attention pooling, which is calculated using these keys and the query here. So let's dive maybe a little bit deeper into the attention pooling itself. So this image is exactly the same one as we've seen before. And we will see three different ways of doing this attention pooling. The first one is average pooling, which will be the simplest one. We will see what's called the non-parametric kernel, the Nadaraya-Watson kernel, which doesn't take any parameters, but we will be able to generate attention for these values. And lastly, we will see how we can do even better by adding a learnable parameter to our attention mechanism. And to start this example, let's just say we would like to learn the following function here. And this is a sine function, basically with amplitude 2, plus a value here, which will depend on the x value, plus some usually Gaussian noise. It's just a noise term, and we don't really have to care about this epsilon here. But how this function will look like, it will be a sinus, but it will slightly drift to the upper side due to the second term, right? So it's actually shown here on the right figure, where we have here in blue the truth values. And in orange here we have the samples which have been drawn from some generating functions based on this truth function. And here we will have some prediction. And let's put aside the prediction for now, but the goal here of this task is really try to predict the blue curve, only having these orange points here to do that. And maybe the most simple, but also worst possible way to do that is just to say, well, I don't really know what this function is, so I'm just going to take all of my orange points here, and I'm just going to average them. And this is average pooling. And mathematically speaking, it's this function because we just take the sum over all of our outputs and divide by the number of samples we have. So it will be this prediction curve here. Sorry. So this is average pooling, but the obtained results on a test on a test set will be unsurprisingly less than optimal. And as you might guess, it's because we don't make use of xi or x, so here the keys or the queries. So we don't make any use of the information on this x-axis because we just averaged over the y-axis. So this is a pretty simple but probably useless model. So Nadaraya and Watson proposed a much better approach. What they proposed is to weight the values according to their input location. And one way to do that is using this formula. And here k is called a kernel. So this is just a function which will return some value here. And it basically takes as input the distance between what is the query and some key value here. And we're going to do that for each key value pair. And we can reformulate this function here to fit the general attention framework. So you can see here that the first term, we can rewrite it and just say this is a function of x which is the query, and xy, which is the key. So we just simplify here. And what we're going to talk about from now on is how this alpha is calculated, this alpha function, so the attention weights. And what this formula is also saying is that what we're doing is we let interact the query with the keys to average or to create weights for the values. And this is exactly what we were doing if you remember this image here. So here, this will be our x. The keys here are our xi, and the values here are our yi, and then we will get the output y. Another thing to note is that the weights generated by the attention scoring function, they will all be valid probability distributions. So they should be non-negative and sum up to 1. But this is more of a detail. And we haven't really talked about how to choose the kernel or what this K should be. And the simplest one we can choose is called the Gaussian kernel. So if you're familiar with the normal function, it's going to look like that. And you here, we will put this K into the formula that we had before. So it will be into this formula here. And what we will get is basically the formula here, where first we get here the exponential, but we have to divide here by all of the exponential for all key value pairs. And if you're familiar with the softmax function, you will see that it's exactly its definition. So in the end, what we will do is the sum of the softmax for the distance between the query and the key squared times this factor here. And an important thing to see here is that the model itself doesn't depend on any parameter. There is no learnable weight, so we can just have our query keys and values, and we're basically good to go. We will get something already better than just the average pooling. And if we do that, that's exactly what we're going to see. The model is doing better than average pooling because you can see here that it tries to fit a little bit better the function than the average pooling, but it's still not perfect. You can see here that especially in this region, there are some gross errors. In this region are some gross errors. And here it's doing kind of okay, but it could be better. And it's true that in this case, if we had more input points, if we had more samples, this kernel would actually lead to better predictions. So it's what's called consistency. The model would get better the more points we had, if we had here to generate the key value pairs. We can also plot the attention weight. So if I come back here, we can plot this value here depending on the query and the key. And what we see is that indeed, the closer the testing input and the training input is, this is the attention weight here, the more red it is. And what it means is that it will pay more attention to those inputs. So we're already getting better results, but it's still not optimal. And a very easy way to render this framework even better is to introduce a learnable parameter. And in this case, it's really easy to do that. We are just going to append here our learnable weight, which will multiply the distance before we take the square root. And it's not going to change the formula by that much, but we will try to train our model to get this W. And if we do that, what you will see is that indeed the predictions get much, much better. And even if when we plot the attention coefficients, we almost get a straight line. It's not perfect, but it's definitely doing better than what we've seen before. So we talked about how to calculate or how the attention mechanism works on a high level basis, but now we're gonna look into how to calculate the attention coefficient. So far we have seen the Gaussian kernel. Um, the Gaussian kernel is an example of a scoring function. And what we did is just to calculate the score and then pass it into the softmax function, because the softmax has the nice property that the output we get from it will be a valid probability distribution. But there is really nothing prohibiting us to use something different than the Gaussian kernel. Everything which takes the query and the keys and calculates a scalar, here A, would actually be valid to generate the attention weights. So we're gonna see how to do it differently. Maybe one thing to point out is that once we have the attention weights, which are the output of the softmax, we're just gonna multiply them with the values and add them up to get our output. And what this basically is that we are just making a weighted sum of the values. And mathematically speaking, it's this formula here where it's just the sum of some attention weights times the value. So this is basically this part here. One very common situation is that the query and key vectors have a different length. And what we can do at that time is to use additive attention. The basic idea here to calculate the score A between the key and the key here and the query is to first use learnable parameters on both the query and the key. Just add everything up such that they have, since they have the same dimension, we can just add them up and pass them through the 10H activation function and multiply it with another learnable vector to get our A's, so the scalars I was showing here previously. So this is really useful in the case where the queries and the keys don't have the same dimension. So we first force them to have the same dimension using these learnable weights. But more efficient scoring function is the scaled dot product. It's the one we will usually see when looking at attention papers. However, that way of scoring will require that the vectors have the same dimension here, since we are taking the transpose and multiplying it here together. And you might wonder why we have to scale it here by the square root of the dimension. It's just that we want to ensure that the variance stays to 1. So that's why it's the scaled dot product. Going to the next topic. Let me just see time-wise. Okay, I have to hurry up a bit, sorry. For the next topic, we're going to talk a little bit about RNN encoder-decoder architectures. I'm not sure we had a look at the encoder-decoder architecture in detail, but the idea here is that the encoder will take tokens, and using an RNN, for example, the encoder will create some context variable or some context representation. And then that context representation is fed into the decoder with the token together to generate the next token, as you can see here. So imagine those are actually these here, these are two different languages. It's important to create the context representation first so that the model knows what the sentence is about, let's say, before starting decoding, and then it will be able to decode correctly in the target language. And we can represent this nicely using this figure here. So again, we have a source, we embed to have a vector representation of our words, and then we pass it through a recurrent neural network to get the context. And the context is fed then to the decoder, which is also an RNN architecture. But one key drawback of this um, framework here, as it's written, is that at each time step, the context variable or the context representation doesn't change. So it doesn't matter what the inputs here or here are. It will always use the same context of the encoder after it has been calculated. And Badenau and all, they saw that this is not the most performant way to do that. So what they propose is to recalculate at each time step the context representation. And the query that they used for that attention mechanism is the uh, decoder hidden state from the previous time step. And for the key and the values, they just use the hidden state of the encoder. So the context representation here at time step um, t t here will just basically be recalculated at each time step, but it uses the hidden representation of the encoder. But what that means is that ct here will be changing at each time step. Effectively, what the model does is to only attend to the relevant input tokens when generating the context. And as you can see here, the context, when it's calculated, is just concatenated with the input values and passed to the recurrent neural network, the decoder. And implementation-wise, we only need to change this part of the model. The encoder basically stays the same. And lastly, I'm just quickly going to talk a little bit about multi-head attention. It comes from the fact that it's very beneficial to allow multiple representation subspaces of the queries, keys, and values. So instead of having only one attention pooling, what we can do is just create several ones. Each is first passed through a fully connected layer here. And each part here is also called a head. And at the end, when we generated all the attention scores, we're just going to concatenate them and pass them through a fully connected layer. So this is why this framework here is called multi-head attention. It's just because we will have multiple attention poolings. Yeah, that's basically it for the theory part. So
I hope you guys can see my screen, right?
yeah, it's working.
Yeah, perfect. So last time we looked at how can we code and implement RNNs, right? So what we usually did is take a document or like corpus and then do some pre-processing, which involves tokenization and vectorization, and then we essentially convert tokens into indexes, right? And then we take indexes and put it inside a one-hot encoding, in which the dimensions is the vocabulary size um, by one for a particular token, essentially. So basically, this is what we looked at, right? So my user pointer. So this is exactly what Pierre implemented last time, essentially. So we had one hot encoded vector, and then we feed it into RNNs, right? And if we look more deeper into RNNs, it turns out it has, of course, 3 bits and input to hidden and hidden to hidden and the hidden to outputs, right? So that was the basic idea behind the RNNs. But now this session is all about machine translation and sequence to sequence model, and we'll see how are we going to implement it. But first, the high level overview of this entire architecture is that we have basically two RNNs. One is encoder and another one is decoder. So encoder takes essentially takes uh, I don't know, a sequence from one language, for example, and then tries to convert it into some other language using a decoder RNN. It's important to note that in encoders, we don't have outputs because we don't need outputs essentially, right? But in decoder, we do need outputs because like that is what we really wanted to predict. So if we look deeper into encoders, we take our X's and insert it into embeddings. So what are embeddings? So basically we take our one hot encoded vectors into some d-dimensional spaces. And why are we going to do that? Because this will allow us to give more representation for future layers to modify essentially. So the composition of one hot encoding vector is not so good as the composition with the embeddings. Once we have the embeddings, we can put it inside our, I don't know, RNN, GRUs or LSTM layers. If we use GRUs, we have two outputs. One is hidden layer at each time step and hidden layer at the last time step. One thing to note that is the dimensions, because like I get confused a lot when I look at these dimensions, right? So the dimensions of embeddings is going to be batch size and number of steps and the embedding size. Embed size, it's the exact D dimension that I talked about earlier. Now in the hidden layer at each time step has number of time step, batch size and number of hidden. Now in the last time step, we have something called num layers. And the reason for that is because now we are using multi-layer RNNs essentially. So the first dimension is all about num layers, and second is batch size and number of hidden units essentially. Now we are going to need all of these information uh, to feed it into decoders, and the decoders will use all of these information in order to predict uh, best possible French word from the given inputs, right? Now with that bits out of the way, let's try to code it essentially. Uh, Here, can you share the starter code file?
Sorry, what did you want?
Yeah, can you share the coding, the notebook? Sorry.
Okay, yeah. Let me share it in the chat.
Thank you so much. And in the meanwhile, let me just import the D2L library. It's the same drill that we have done for a couple of times, essentially. Now, the first thing we are going to be implementing is classical sequence-to-sequence model, which doesn't involve attention. And then we will essentially use that and build upon that in order to create sequence-to-sequence with attention model. So let's get started. Let me remove the things that I don't really require. And first, as I mentioned earlier, we are going to require embedding layers, right? And PyTorch has its own embedding layer, which is called an embeddings, which takes two inputs, vocab size and embed size. Now, the vocab size is exactly what we've seen earlier. Like for example, if we have character level RNNs, then your vocab size is going to be like, I don't know, 24 plus 5 or 6, right? And those 5 or 6 are going to be special characters. And 24 is of course because A to Z is your number of characters, right? So these are your entire vocab. And embed size is, as I mentioned earlier, the dimensionality of your embeddings. With that, let me introduce our RNN layer. RNN layers, this time I'm going to use GRUs, and it requires us 3 arguments essentially. One is embed size and number of hidden layers, a number of hidden units, and third one is the number of hidden layers. And I'm just going to dropout. Like the basic idea of dropout is that it is used for regularization, and the way it is able to do that is by just switching off some of the neurons, right? Now with that, let's start with the forward pass. Uh, Forward pass require us to just take our input vectors, and the input vectors, the dimensionality of input vectors, let me add it here. It's going to be a batch size and number of steps, right? That is one more thing that I would like to highlight is number of steps, which means like of course how long a sequence is going to be. And one thing to note is that if the sequence is smaller than the specified maximum sequence, then it's going to use padding essentially. I guess that's it. Now let's look at our next step, which is first we are going to need to permute it, and the reason for that is because our GRU layers requires us to have the number of steps as the first dimensions. So with that gets out of the way, let's yeah, so here I've used outputs and state. So this is exactly what this is essentially. So one is the hidden layer at each time step, but that doesn't give you the hidden layers or all the entire hidden layers. It is only give you the final hidden layers essentially. But in the hidden layer at the last time step, we are going to be getting the number of layers in its entirety as well. Now with that, okay, so let me add the shapes of it. Steps, batch size, okay, and the shape of state, as I mentioned earlier, is going to be number of layers, batch size, and number of layers. Lo and behold, it should work. And it's working perfectly. So as you can see, the output shape is exactly what we are expecting, which is number of steps and path size and the number of hidden. Right, so number of hidden is here. Yeah, so this is path size essentially, and this is the number of steps. So currently, it's of course it's a dummy test. We will look into how can we predict English to French as we move along. Now that we have implemented our sequence to sequence encoder, let's look into decoder part, right? So decoder is a bit more involved essentially, but the basic idea is the same. So we have R1 hot vectors, right? And we inject it into our embedding layers, and then we use GRUs and take embeddings as our inputs, which will give us a hidden layer at all time steps and hidden layer at the last time step of the of all layers in our RNNs. Now we are going to use hidden layer at all time step and inject it into dense layer, which will give us the output. So this is the prediction part. This essentially gives us the prediction inference. Now again, for sanity check, these are the dimensionality, or these are the shape of the outputs that we are expecting. Let me remove this and start the decoder part. And the drill is exactly this. And less verbose this time. And our final property. Now for initializing our decoders, I have also pre-implemented the init state, right, which takes this function and takes the first element of this function of this array. We will look into this one in later part. This part is but the basic idea is the same, right? So we have embeddings, and then we injected outputs from the embedding layer into RNNs, and let's do that. So first we are going to give inputs again. Of course, as I mentioned earlier, since our RNN requires us to convert, we have to follow that essentially. And yeah, exactly. So I should have mentioned this, but it also requires context vector. So in the attention layer, the query vector can be thought of as our context vector. I will talk more about it as we move along. So, now, the state here is exactly the state that encoder gives us at this time, right? Because as I mentioned earlier, these are essentially all of the weights of all of the layers and its hidden unit at the last instant. So we will use that and call it a context vector essentially, and put it inside our decoder, which will help us to essentially give context of the sequence that we are encoding. Right. So the advantage of that is, of course, now that we have some context about what exactly that we need to decode, right? We need to translate inference. We can do a better job because we have this context. Now we take x and context vector, which means we concatenate the inputs and the context vector. and put it inside our RNNs. Now that we have our RNNs, so as I mentioned earlier, these these things give you the weights of hidden layers at all of time steps, right? And since we need to predict the best possible French word at all of the time step, we are just going to take the values of the hidden layers and just put it inside our dense layer. So this is exactly what we did uh, here, right? So we took all of the hidden layers and its values, and then use a dense layer to predict a particular value from these information at a particular time step. I, yes. Now we take dense layers, and this will give us the uh, predictions, or I should say logics, basically. So we are going to use that and transform it into probabilities, basically. Although we can do that here, but the book prefers it to do it when we are predicting or when the output shapes. So let me just write it down for the sake of it. And state is exactly the number of layers, patches, and number of layers. Now with that, let's hope it works. First of all, just let me check. Okay. Oh yeah. So we have it initialized on dense layers. Sorry about that. So dense layers are nothing but fully connected layers. It's just a more fancy way of saying. One part is not defined.
I think it's context,
Yeah,
right?
context.
It's context, yeah.
Yeah, and lo and behold, it's working. Now with that gets out of the way, let's test our classic encoder and decoder. So, it is first downloading the NMT data, which comes with the G2L, and then it essentially initialize our decoders and encoders, right? It takes the output from the encoders and of course put it inside the decoders, or it is being done implicitly by this encoder-decoder architecture, which is given by D2L. And once we have the network, right, we can just essentially, and it is done. For testing, I'm just going to use 4 sentences, right? and one in English, and another one is in French, right? And it essentially tries to convert English sentence into French, right? Uh, and what are these essentially? So these are the metrics that we are following. So Blue Score has a really nice history about it. But okay, so let me briefly talk about Blue Score. So the basic idea of Blue Score is it tries to give you a metric in which if you are able to give me the best possible outputs, right? From, of course, your true labels from the predicted labels, essentially, right? Then I'm just going to give you a Blue Score of 1, right? Uh, but if you are giving me prediction on smaller sequences, right? So I'm not going to reward you that much. So that also includes some penalty terms. But if you are able to correctly predict or translate English to French, for example, right? Uh, if you are able to correctly predict the longer sequence, then I'm going to reward you even more. So that is the basic idea behind Blue Score, and it is abundant in natural language processing. But I have to I would love to talk more about it because there are a lot of different architectures that moves even beyond the best possible Blue Score attained by even humans, right? So people are still trying to figure out what is the new metric that they should train on, for example. Right? But it is highly experimental at this case, so let's not go there. Let's stick to our Blue Score. And since it doesn't do a good job at converting Go into French, then your Blue Score is confused, right? Uh, so as you can see, the Blue Score is not that good with our current architecture, right? And to the rescue, we have sequence to sequence with attention models, right? So let's talk about attention. Right? Although I think Pierre did a great job at talking about it, but just it doesn't hurt to read that, right? So we have the basic idea of encoder and decoders, right? We take the source and put it inside our embedding layers, and then we have different layers. Now, at each hidden layers, right, or at each time steps, essentially, we are just going to take weighted linear combination and put it inside a nonlinear function. This will give us what is known as attention weights, right? Uh, Now, why are we doing that? The reason for that is extremely simple. Now, for example, if I say a sentence, MLT is an awesome community, right? Which it is. So when I use RNN layers, right, the importance that I give at a particular time step uh, or at the previous word of the current time step, then I will lose most of the information that I have already collected previously. Uh, so attention is saying that give me all of the words that you swipe through uh, at all of the time step, and I will tell you that which words you should care about, essentially. So the advantage is that now we don't have to worry about longer sequences, right? And forgetting about this, we can just use attention layers, and that attention layer is telling you that you should focus on this word, not the other word, for example, right? And once we find code attention layer, essentially. There are multiple attention layers, of course, additive attention, and of course, Nadaraya-Watson kernel. So when I first look at that, I was shocked. What is it doing here? But it kind of makes sense because, like, of course, you are taking weighted linear combination of it, and of course, getting the weights out of it, right? So adding a kernel doesn't hurt, and it always is beneficial, I guess. Now, sequence to sequence with attention encoders. So the idea is exactly the same. So we are just going to use the exact same encoders of what we've coded, right? But decoder part is going to be a little bit more involved. Here is the entire idea. So you have hidden layers, right? Of the encoders, right? We are denoting it as HT, and the state of your decoder at 0th time step is going to be the hidden layer, or the values of your hidden layer at the last time step, right? So this is exactly what we talked about earlier, right? So we are just using all of the states of the last time step from the encoder and put it inside decoder, right? But it is not so straightforward in attention decoder, right? Because we need to give this guy as much information as possible, right? In this framework. Now, the context vector is going to look like this, right? So this is just a weighted combination of your hidden layer, and the weights are being calculated as follows, right? Once we have the context vector, we can just use our vanilla RNN or GRUs, for example, right? In order to calculate our current state of a particular time step of decoder, right? And once we have that, it is straightforward to see how can we get the outputs and get the best possible prediction or best possible French word in a particular time step. With that gets out of the way, let's start coding. So yeah, I'm just going to remove this because we have time. So I thought we haven't got much time, but luckily this time we actually do. So yeah, good stuff. Yeah, so additive attention, as I mentioned earlier, the way to calculate our attention weights is as follows, right? So here we are using 3 weights, and then these weights are going to get learned, just like we always do whenever we use weights, right? So let me try to re-implement it. So again, let me initialize the weights of all the weights that is required, that is presented in this additive attention weights framework, essentially. So use, key size. Yeah, so here is the entire idea of keys and values come about. But like to me, that was a bit more confusing analogy. So I always think of it in terms of weights and just a weighted linear combination. And this should most of the time gets the job done. So here we are not using bias, although you can use that, but I'm not going to do that. And we're taking the number of headings. pi is equal to false. And again, let's follow this exact analysis. Queries for keys, we have this. Right. Correct. For features, we are just going to use queries and do unsqueeze, and the reason for that is because we need to expand the dimensions, right? And then broadcast them and sum them up, right? And for dimensions to work nicely, we need to unsqueeze. So for sports, we're just going to use this guy. And since we've already calculated this, we can just do matrix multiplication. Okay. It is internally doing matrix multiplication, right? Because like it's linear layer, so it is the operation. Now again, there's only one input for. Oh, sorry, I should say there's one output of the W, right? So we remove the last one dimension from the shape. Right. So okay. So let me add dimensional information at its right side. So one is batch size, then second one is number of queries, of key value. Right. And finally, let's just go to sorry. Now, although I haven't talked about mass transformer, so let me talk about it. But first, let me finish this line. Yeah, so the basic idea of mask transformer, masked softmax is essentially it's just the same softmax that we all know and love, but it is masked. And the reason for that is, for example, if the sequence is smaller than our maximum sequence, right? So we are going to pad it, right, with some arbitrary value. And that value or that word isn't going to have much significance, right? So in order to remove whatever gradients or whatever values come out of those padded uh, padded indexes or padded tokens, right? we are just going to have to rule them out, right? The way to do that is to just mask out all of those unwanted values. That is the reason why we are using mask softmax, right? Uh, Now, how do we know that which one to mask or not, right? So we are just going to take all the scores, and we are going to provide this entire function when we call it a valid links function, I guess, right? Now with that, we have our scores, right? And then we masked out all of the unwanted scores, and that will give us the attention weight, which is exactly that what we need, right? So BMM stands for batch matrix multiplication, and then just we are going to check it out. I think it should work fine. Let's see. So let's hope for the best. Oh, don't hope for the best. This is good. Additive potential of the plus RWP.
I think this is capital W, self dot capital W underscore V.
Oh yeah, thank you so much.
And also the spelling of lens, the valid lens is not consistent.
Sorry. Thanks. Now, yeah. Oh. Okay, so of course, why not? Should go. Yeah, thank you so much, guys. And now, if we look into attentions, right? So these will give you the visualization, a really nice visualization of attention weights of all the keys and queries that we put it inside our attention function or model. Right? So this is exactly what we want, right? So we give them some keys and we have some queries, right? So for that we need to essentially ask what weights should I give to my queries, right? Uh, in order to hopefully in future, of course. Currently, it's not good on its own, but hopefully using these weights, we can find a better context for our decoder so that we can get the best possible output at a particular time step. But the basic idea is the same, right? So the concept of keys and queries still holds here, and it will still hold as we look into real cases. Now, finally, that we have our additive attentions, right? we now need to create attention decoders, right? So I guess, yeah, I talked about it. Right? So basically, this is the entire idea behind attention, right? But I like this picture a little bit because it will give you most of the information that is required for me to understand, like what should I code. Right. So without further ado, let's essentially put it into reality. Yeah, by the way, how are we doing with the time?
We're good. We still have about 10 minutes left.
Oh, so I'm literally on the edge. That is good. That is good. That is good. Yeah. So exactly. Let's quickly implement it because we've seen most of the things that we need to know for us to implement decoders, right? So I'm just going to run through it. The first thing is, of course, for it to have a really nice programmatical overview, right? We need interfaces, right? So this is exactly the format that it will uses. So let me respect that. So we take a decoder class, right? So it's just going to be an interface, and then we have an interface for the attention decoder. It is doing nothing; it's just giving you an entire structure, right? It's an interface. Let me remove the things that I don't need, and let me add things that I do need. So attention, we are just going to take attention, the exact thing that we have implemented up till now, right? And give them all of the arguments that this requires. We have set wedding. We have an attention layer, a wedding layer. I don't know, is it safe to say it there? I'm not sure. But anyways, we have a wedding layers. Size. So use we take the embed size plus the exactly like what we did earlier. It is a number of computers. Drop out. Okay, so I will implement it later. First, let me finish the forward pass. So we are just going to take the encoder outputs and the hidden state and encode valid lengths. The axis, put it inside embedding layers, and again we need to permute it because that's how our RNN likes it. And now the most important part is that we are going to use loops, right? And we are just going to go over for each time steps, right? and take the hidden units, and then do the weighted linear combination. We are basically using attention and put all the outputs inside it, which will give us the best possible context vector, and then we're going to use that context vector and put it inside our encoder state at a particular time step. Yeah, so another thing, it is important to note that the X here is not going to be English, it's going to be French when we use it to translate from English to French. Dimension vector is and of course, as I mentioned earlier, we need to concatenate these two guys.
Mirtan, yeah, sorry to interrupt. It was pointed out in the chat that actually there is a typo on line 16, the self. You wrote slef. Yeah, thanks to
Yes, thank you so much.
Ahmed.
Yeah. I'm racing against time here, guys. Anyways, yeah, so now we need to concatenate our context vector, and of course, I'll squeeze this guy. And it requires one more dimensions. At what dimension do we need to concatenate? It's going to be class. State. So, which is just our group related to current unit and compute. And append all of our outputs. This variable, output variable. Right. Now, as you can see, okay, so let me first type everything out. Then I'll talk more deeply about the things that I have here. Attention. Take the attention weights. Right. Right. And I guess that's it for this loop, right? So it's sorry about that. Return outputs. Again, why are we permuting it? Because that's the embed. That's how embedding layers, or that's how we are specifying it. Right? So we want number of time steps to be the first dimension, right? And then batch size, and then vocabulary size. I'm just going to use arrays. So I have encode outputs. What is encode outputs? Let's see if it works. Of course. state. Sorry. Sorry, I haven't implemented the initial state. Right, so the initial state is exactly the mostly it will be the inputs and some of the initialization, like for example, some of the weight initialization that we need, right? But of course, it's going to be in this case the encoder, the outputs of the inputs. New so okay. Oh, tension weights is not implemented. Yeah, another thing that I forgot to implement, but it is important. So it's just going to be the attention weights. The decoder part. Finally, it is working as we expected. And we are at the top of the hour. So let me just run these two slides and then congratulations. We have implemented our own sequence to sequence architecture with attention mechanism. And as you can see, it is running pretty exciting. Yes, I can talk a bit more about this, but if there's any interest, but I guess that's it. We'll let this guy finish and then we'll look into tests. Right? We are just going to use the exact same data set, quote unquote, and see how it will perform. And yeah, so we can use attention model to do sequence to sequence, right? We can also use attention model to do image captioning, which I was quite excited about when I first learned it. But for now, okay, let's look at our results, right? Let's look at our sequence to sequence model with attention. And as you can see, the blue score is 1. So like it is doing a really great job, even if the data set is really small, right? So this is not quite I was expecting, but this turns out to be the case. So that means all of the hard work was worth it, basically, right? Yeah, so I should just suck out the fun. Convert to the device type to file. I don't know why it is important. Okay, so I think my time. I don't want to change the time type. for now, because but we did exactly what we need, right? So I'm just going to switch I don't know, our final output, so that will give us a good picture.
Maybe J, we can just show if you have the notebook,
Yeah, exactly.
which already has the picture.
So I just want to see if it's a long problem to fix for a short problem. But yeah, basically we did exactly what we were supposed to do essentially. So if we were to plot our heat map, which shows the attention weights for your key position and your query position, then we can see how is it working. So although it's a bit convoluted in this picture, right? But I have this one, right? So basically, this is English and this is French, right? Now, in the original sentence, the reason why it is given more weights into this, right? So it is essentially saying that swipe the European economic with economic European, right? So which give us a really good idea that it works as we expected it to be, right? And the reason for that, because it also takes into account uh, words that has come before, which should influence more the prediction that is about to come, right? So that switching is also taken into account because we've used attention mechanism. So attention mechanism is a really powerful tool, and that is the reason why people are using it. But I guess another example would be right. So we can also use this exact same analogy, right? And instead of decoders, we can use CNNs, right? RNN decoders. We can use CNNs, and what it will give you is given the images, it will tell you the contents of the images. When I first look at this result, I was blown away, but this is possible. That is quite interesting. So I guess that's it from my side. Maybe we can start with the discussion part. One thing maybe I would like to highlight that attention is not the only guy. There's a new guy in town, which is known as CapNet, which use Fourier features instead of attention, and it is a bit more efficient than the attention, but attention has been good to us for now, and that is the reason why it is important even today's day and age. So that's it from my side.